In this video, we are going to discuss about low-pass filter. Filters, as name suggests, they filter the frequency components. That means they allow certain frequency components and reject some other frequency components. Filters are frequency selective networks that attenuate signals at some frequencies and allows others to pass. Filters are characterized by passband and stopband. Passband is the band of frequencies of the input signal that passes through the filter with attenuation, while the stopband is a band of frequencies of the input signal that are blocked or more highly attenuated by the filter. Filter networks is constructed from reactive components, that is resistor, inductor and capacitor. Filters are widely used in electronics and telecommunication to separate various channels. Mostly they are used in radio, television, audio recording, radar, control systems, music synthesis, image processing and much more. Filters are mainly classified into 4 types based on the band of frequencies that are allowing, band of frequencies that are rejecting. Following are the types of filters: low pass filter, high pass filter, band pass filter and band stop filter. Low pass filter, as the name indicates, it allows only low frequency components and rejects all high frequency components. High pass filter allows only high frequency components and rejects all low frequency components. Band pass filters allows only one band of frequencies. In general, this frequency band lies between low frequency range and high frequency range. That means this filter rejects both low and high frequency components. Band stop filter, as name suggests, rejects only one band of frequencies. In general, this frequency band lies in between low frequency range and high frequency range. That means this filter allows both low and high frequency components. Low pass filter allows all frequencies up to certain cutoff frequency, that is FC, to pass through it and attenuates all other frequencies above FC. High pass filter attenuates all frequencies below FC and allows all other frequencies above FC to pass through it. Band pass filter allows a limited band of frequencies to pass through it, that is between FC1 and FC2, and attenuates all other frequencies below and above the frequency band. Band stop filter, it is just opposite to that of band pass filter. Figure shows the characteristics of the ideal filters. Low pass filter. In this, the passband lies below the cutoff frequency and stopband exists above the cutoff frequency. High pass filter, passband lies above the cutoff frequency and stopband lies below the cutoff frequency. Band pass filter, passband lies between FC1 and FC2, while the stopband lies below FC1 and above FC2. While in band stop filter, stopband lies in between FC1 and FC2 and passband lies below FC1 and above FC2. In this video, we are going to discuss about low pass filter in detail. Basically, we will be having 2 types of low pass filter. One is constant K low pass filter, another one is M-derived low pass filter. A T or pi network is said to be a constant K-type filter if Z1 and Z2 are opposite type of reactants, satisfying the relation Z1 into Z2 is equal to K square, where K is a constant which is independent of frequency. K is often referred to as a design impedance or nominal impedance of the constant K filter, which is used to characterize a filter. K is nothing but design impedance or nominal impedance of the constant K filter. Usually, low pass filter can be either represented in the form of T or pi section filter. The main disadvantages of constant K filters are the attenuation is not sharp in the stop band and the characteristic impedance varies widely in the pass band. This can be overcome by M-derived low pass filter. Constant K filter is also known as prototype filter because all the other forms of filters can be derived from constant K filter. Now let us discuss in detail about low pass filter. Figure shows T section and pi section of a low pass filter. Now, for a low pass filter, consider Z1 as inductive reactance while Z2 as capacitive reactance. That is Z1 equal to j omega L, Z2 equal to minus j by omega C. First, we'll derive the nominal impedance and cutoff frequency for a low pass filter. Nominal impedance can be found by the relation K is equal to square root of Z1 into Z2. We can substitute from the previous equation, that is Z1 equal to j omega L and Z2 equal to 1 by j omega C, which is equal to square root of L by C. And cutoff frequency can be obtained when Z1 by 4Z2 is equal to 0 and Z1 by 4Z2 equal to minus 1. Using the first condition, that is Z1 by 4Z2 equal to 0, we can prove Z1 is equal to 0 and hence omega equal to 0, which in turn frequency will be equal to 0. Using the second condition, that is Z1 by 4Z2 equal to minus 1, can obtain omega square is equal to 4 by LC, which in turn omega C will be equal to 2 by square root of LC, which in turn cutoff frequency will be equal to 1 by pi square root of LC. Thus, cutoff frequency for a low pass filter will be 1 by pi into square root of L into C. L is nothing but value of the inductor and C is nothing but value of the capacitor. Now we can derive attenuation constant for the low pass filter. In the pass band, alpha will be equal to 0 and in stop band, alpha will be equal to 2 into cos h inverse square root of Z1 by 4Z2. Again, substituting for Z1 and Z2, we can get alpha is equal to 2 into cos h inverse of f by fc. That is, figure shows the characteristics of attenuation constant with respect to the frequency. Attenuation constant alpha is 0 throughout the passband but increases gradually from the cutoff frequency. Next, we'll derive phase constant for the low pass filter. In passband, beta will be equal to 2 into sine inverse square root of Z1 by 4Z2, that is equal to 2 sine inverse f by fc. In stop band, beta will be equal to pi, that is it will be that figure shows the phase constant versus frequency characteristics. Here, beta will be equal to a constant in the stop band while it varies in the pass band. Okay. We can see the attenuation constant will be 0 in the pass band, okay, while beta and the phase constant will be varying in the pass band. Similarly, the attenuation constant in stop band will be varying while in the phase constant will be constant in the stop band. Next, we can derive the characteristic impedance for the low pass filter, both for T section as well as pi section. Characteristic impedance for T section is given by Z2T is equal to square root of Z1 square by 4 plus Z1 into Z2. Okay. Z1 and Z2 are impedances or series impedances and parallel impedances. By substituting Z1 and Z2, Z1 as j omega L and Z2 as 1 by j omega C, we can obtain Z2 as k into square root of 1 minus f by fc whole square. While for characteristic impedance of pi section, Z1 into Z2 by Z2T. By substituting for Z1 and Z2 and Z2T, we can obtain Z of pi will be equal to k by square root of 1 minus f by fc whole square. And the characteristics of ZOT and ZO pi is given in the figure. The characteristic impedance ZOT is real when f is less than fc. At f equal to fc, ZOT is 0, and for f greater than fc, ZOT is imaginary in the stop band, rising to infinite reactance at infinite frequency. ZO pi is real when f is less than fc. At f equal to fc, ZO pi is infinite, and for f greater than fc, ZO pi is imaginary. Now let us see the design of the low pass filter. We have obtained k previously. The value of k is nothing but square root of L by C. K is nothing but nominal impedance. L is nothing but value of the inductor, and C is nothing but capacitor value. Fc is nothing but cutoff frequency for the low pass filter, which we have derived just now, which is nothing but 1 by pi into square root of Lc. Using these two values, that is design impedance and cutoff frequency, we can obtain the values of L and C as below. The value of inductor will be k by pi into Fc, while the value of capacitor will be 1 by pi Fc into k. Figure shows the T and pi section of low pass filter. Here in low pass filter, we will be having inductance in series while capacitance in parallel. In T section, the values of inductor will be L by 2, and the value of C will be as such C. In pi section low pass filter, inductor value will be L and capacitor value will be C by 2, as shown in the figure. Figure A shows T section low pass filter. Figure B shows pi section low pass filter. Now we'll discuss some of the problems based on this. Problem 1. Find the nominal impedance, cutoff frequency and pass band for the network shown below. The network is given here. From the figure, clearly it is known. This filter is low pass filter. That is, we are having inductance in series and capacitance in parallel. The value of the inductance is 25 millihenry and the value of capacitance is 0.2 microfarad. Okay, the answer to this problem is, here it is asked nominal impedance, cutoff frequency and pass band for the given network. Okay. From the figure, we can obtain the L value. Okay, clearly we know this is T section. For T section, the value of inductance will be L by 2. From this, we can obtain the value of L as 50 millihenry, and capacitor value remains as such. C will be equal to 0.2 microfarad. Okay. With this, we can find the nominal impedance, cutoff frequency and pass band. Nominal impedance for low pass filter will be k is equal to square root of L by C. Substituting the values of L and C, we can obtain the k value as 500 ohms. Second, the cutoff frequency. Cutoff frequency for low pass filter will be equal to Fc is equal to 1 by pi square root of L into C. Substituting the values for L and C, we can get 3.18 kilohertz. Now, nominal impedance k will be is equal to 500 ohms and cutoff frequency will be 3.18 kilohertz. Now the pass band. Since this is low pass filter, pass band will be from 0 to cutoff frequency. Here since the cutoff frequency is 3.18 kilohertz, pass band will be from 0 to 3.18 kilohertz. Problem 2. Design a constant K low pass T and pi section filters having cutoff frequency of 4 kHz and nominal impedance of 500 ohms. Given values are cutoff frequency will be equal to 4 kHz and nominal impedance K is 500 ohms. Here we have to design both low pass T and pi section filters. We know that For low pass filter, the values of L and C can be obtained with the help of formula. L will be equal to K by pi Fc and C 1 by pi Fc into K. Substituting the values for K and Fc, we can obtain L is equal to 39.79 millihenry. Capacitance value will be equal to 0.16 microfarad. And we can draw the T-section low pass filter by having the inductance value. For T-section low pass filter, inductance will be in series having the value L by 2. Here, since L is 39.79, from this we can obtain the L by 2 value, that is 19.9 millihenry, and capacitance value remains as such. C is equal to 0.16 microfarad. And figure A shows T-section low pass filter. Okay, similarly, we can obtain for pi section low pass filter as this. That is, here inductance value will remains as such and the capacitance value will be C by 2. Okay, that is L will be equal to 39.79 millihenry and capacitance value will be C by 2, that is 0.08 microfarad. Figure B shows pi section low pass filter. Yes. Okay, I think by now you'll be getting some idea about low pass filter and how to design low pass filter, and you'll be able to solve some of the problems with this. Thank you.